All right, hey Alex. So thank you for turning in the previous assignment. I will check that over and get back to you in a minute, but I wanted to get this out to you as quickly as possible. This lesson's a little bit longer, so this video will probably take a little bit more time to get through. You may want to split it up over a couple of sessions if you get bored, etc. But I will try to make it as clear and concise as possible. So last class we talked about calculating the correlation coefficient. Now we're going to talk about creating a straight line equation with a slope and an intercept that best describes the relationship. Hey, that happens to be called a least squares regression line, or we're probably just going to simplify it and just call it a regression line. But basically, we're going to get an equation. So we're going to go back on some of your algebra stuff. In algebra, you learned about straight line equations, and most of the time, those are probably put in slope-intercept form. And they use this letter M to represent the slope for some reason. They use the letter B to represent the value of the y-intercept. Ym and yb, difficult to say. I'm not 100% certain either. But we could also, instead of M, we could call the slope A. We could also reverse the order in which we wrote the y-intercept and the slope. We basically end up with this version of a straight line equation. This is what we prefer in statistics class. Again, the coefficient in front of your x variable is going to be the slope, and the constant value is going to be the y-intercept of that. In this equation, though, for statistics, there's going to be this little hat above the y, because what this is going to be telling us is this is going to be making a predicted or a prediction. So we read that as predicted y is equal to the value of the intercept A plus the value of the slope B, and then x, of course, is our explanatory variable. All right. So in this example, if we look at a Ford F-150 pickup truck, if you were to be selling this truck as a used car, typically the more miles on the car, the less expensive that car is going to be. So if we went in and found, like if we went on autotrader.com and found a random sample of 16 Ford F-150 Super Crew 4x4s on there and gathered two sets of data, okay? The explanatory variable is going to be the miles driven, and then the response variable is going to be the price of that truck that's listed on there. Okay, so you have these different miles driven correlated with the different prices. If you plot that into a scatter plot, as shown, you can see that the blue dots there, they are negative, right? The relationship is negative. It seems to be moderate, doesn't seem to be super strong, but it probably is best described as linear. So therefore, what we can do is use some computer software or some calculator software to create what we're going to define as the line of best fit, or this regression line. And in this case, that's the equation of the specific regression line that's describing the relationship here in these Ford F-150s. Okay. Now, if you look at the blue highlighted question here from Mr. Wankowitz, it says, predict the cost of a Ford F-150 that has been driven 100,000 miles. Okay, so this Y hat is representing the predicted cost of this truck, and it's best represented as $38,257 minus 0.1629x. X is miles driven. So if we specifically wanted that to take the value of 100,000, then we'd have 38,257 minus 0.1629 times 100,000 is 16,290. And if you use the calculator to come up with the difference there is $21,967. So based on the relationship in the data, if you were to find a Ford F, whatever it was, Ford F-150 Super Crew 4x4. It has 100,000 miles on its odometer. You're going to predict that that truck should sell for about $22,000 based on the regression line data that we have here. Now, can we predict the price of a Ford F-150 with 300,000 miles driven on it? Well, of course we can. We can just plug and chug like we did on the previous one. Y hat is equal to 38,257 minus 0.1629 times X, where X is representing miles driven. So plug in 300,000 for X, 0.1629 times 300,000 is 48,870. Subtract those things, you get a negative answer here of negative $10,613. Well, I'd love to find a truck that sold for negative $10,613. Hey, that doesn't make any sense. Hey, obviously you can't sell a truck for a negative amount of money. So what happened on this one? What happened is we used this fancy term called an extrapolation. And when we extrapolate, we're making a prediction far outside the interval of X values used to obtain the line. So if you look back, if we scroll back up to the original data set, it appears that we have information on what happened of trucks that have been driven just a little bit more than zero, so maybe like 5,000 miles or so, up to what appears to be trucks that have maybe been driven about 150,000 miles. Hey, we have no data on any trucks driven anywhere near 300,000. So therefore, we cannot assume that the pattern continues out to a X value of 300,000. So when you make a prediction for an X value far outside the interval of X values used to obtain the regression line, you can do the math. Like, there's nothing wrong. We can plug and chug and do all the math. But the predictions are often not accurate, and I would say they are certainly always not trustworthy. Now, even when we don't extrapolate, okay, that means we are making a prediction inside the interval of X values we're given. The predictions are rarely perfect, like basically never, right? We're getting a prediction, but that prediction is going to be off by a little bit. In statistics, what we call that error, that how much we're off by, here is going to be called a residual value. The residual is the difference between the actual value of Y and the Y predicted by the regression line. Or in symbolism, residual equals Y minus Y hat. Okay? It's going to be the actual Y value, what really happened, minus the predicted Y in terms of what did our equation predict would happen. So again, if we go back to this Ford F-150 truck, let's say instead of the two examples we've used so far, let's say this truck has 70,583 miles on it. Okay, if you plug that into the equation, you get a predicted price of $21,994. I'm sorry, I said that wrong. There was an actual truck. So when we did our research, there was an actual truck that had 70,583 miles, and the individual who sold that actually sold it for $21,994. Our equation, the least squares regression line, if we plugged in 70,583 miles, it's going to get a predicted sale price of $26,759. So the symbol Y represents the actual. So in reality, this thing actually sold for $21,994. Y hat is the predicted Y value. So the equation predicted it would sell for $26,759. So it actually sold for less than what we would have predicted, right? Maybe the paint was not looking good. Maybe it needed a brake job. You never know. There's reasons why this truck sold for less than what we would have predicted. If you look at the graph, hey, the actual value is an actual data point. That corresponds over here to that actual sale price of $21,994. The predicted value is what is the corresponding value on the least squares or on the linear regression equation for 70,583 miles. If you read that over, right, that is going to be the predicted value of about 26,759. The difference between those, the distance between the actual and predicted value, is called the residual. So here, the residual value equals actual of 21,994 minus the predicted price of 26,759. That's a difference of negative $4,765. Okay? So the fact that the residual is negative means that the predicted value was larger. It also means that the dot itself, the actual value, was below the least squares regression line. All right, tapping on soda cans. You might know what we're talking about in this example. If you shake up a can of soda and then open it, there's probably going to be a bunch of soda spray that comes out of that can. Okay, so students did an experiment. They vigorously, I love that word, vigorously shook 40 cans of soda and randomly assigned each can to be tapped for 0, 4, 8, or 12 seconds. Then they opened the can and, cleaning up the mess, they measured the amount of soda left in each can. Okay, so after the spray, after the eruption, they carefully measured how much soda was left in each can, measured in milliliters. You plot all the data where the tapping time was the explanatory variable, the soda remaining in the can is the response variable. You get these dots that are stacked on top of each other because, remember, they tapped several cans for 8 seconds. So each one of them gave its own readings. You take all the data, you use some computer or calculator software, and you come up with the least squares regression line given here, okay, where y hat is representing the predicted amount of soda left in the can is equal to 248.6 plus 2.63x, okay? Whoops. So, I'm sorry, the explanatory variable is tapping time, because after you shake up the cans of soda, you then tap on the lid for 0, 4, 8, or 12 seconds, because sometimes tapping on the lid seems to like dissipate all the foam in there. So the more taps in general, the more soda was left in the can after you open it up. So sorry for my trying to go fast. I'm kind of misreading some of these things. Okay, so part A says calculate the residual for the can that was tapped for 4 seconds and had 260 milliliters of soda remaining. So the 260 that they gave us, that's what actually happened. The predicted value, y hat, is going to come from the equation. So y hat would be equal to 248.6 plus 2.63x, where in this case you tap for 4 seconds. Now, grabbing my calculator, I'm just going to do the arithmetic here. 248.6 plus 2.63 times 4 is 259.12 milliliters. So the residual is actual minus predicted. So in this case, there actually was 260 milliliters of soda remaining. We predicted there'd be 259.12. So the difference there is 0.88 of a milliliter. Okay, assuming I did my subtraction correctly there. Okay, just scrolling through here to make sure I haven't missed anything. All right, now B, interpret the residual. Okay, so as we interpret the residual. It's a positive number, okay? So if you compare the actual to the predicted amount, we could say things that there was 0.88 milliliters more soda remaining in the can than predicted. Or you could say that you underestimated the amount of soda remaining in the can by 0.88 milliliters. A couple of different ways in which you can word that interpretation. Okay. Oh, here's the template for what I answered above. All right, now, how to interpret a regression line. So when you took your algebra classes, you learned about intercept and you learned about slope, but you didn't really learn enough about intercept and slope, as well as we now need to take it from a statistical perspective, knowing that when we do our predicted values, the predicted values are rarely perfect. So when we talk about the y-intercept, like in algebra, you probably would have talked about that that's where the line hits the y-axis, okay, which is true. But the better interpretation, the statistical interpretation, is that the y-intercept is the predicted value of y when the x value takes the value of 0. The slope, you probably remember lots of things about slope. You might remember slope as rise over run, change in y over change in x, etc. Okay. The steepness of the line. When I talk about slope, when I teach slope in statistics, I refer to it mostly as the change in y over the change in x. But specifically, it describes the predicted change in y for each time there is a 1 unit increase in the x variable. Okay? The good news is, what that now means is that we can put actual meanings into the intercept and the slope in actual real-world context. So let's go back to the Ford F-150 example, where y hat equaled 38,257 minus 0.1629. Okay? Now, the slope, which is this negative 0.1629 value, when we talk about the value of the slope, it's going to be the change in y, which in this case was the change in the price, over the change in miles driven. If we take that slope, which even though the slope is an ugly decimal, which you never saw in your algebra classes, in your algebra classes, your slopes were always nice, convenient numbers like 1/2 or 2/3 or something like that. But if we take that slope, even though it's a decimal, and we write it as a unit fraction, meaning over 1, what this is basically telling us is for every 1 additional mile that the truck has been driven, the price is decreasing by approximately 16 cents or so, or 0.1629 of a dollar. So if we look at how it was worded up here, the predicted price of a Ford F-150 goes down by $0.1629 for each additional mile that is driven. Okay? It's really important that we put the word predicted in there, because it doesn't mean that for every F-150 the price goes down by 16 cents a mile. This is a prediction based on all the data we have. So it's not perfect, right? So this is going to be the predicted decrease in the price. It's going to go down about $0.1629 for every 1 additional mile that it has been driven. Okay? The y-intercept value of 38,257, that's always going to be the predicted value for y when x equals 0. So again, it's a prediction. It doesn't mean it's perfect. But if a truck's been driven 0 miles, we're predicting it's going to sell for about $38,257. Or basically, this would be the predicted price for a new F-150 truck, because new cars have been driven 0 miles, basically. Okay? But again, making sure we're using the word predicted in each of those explanations. So in the preceding example about tapping on cans, the equation of the regression line is given. X is tapping time measured in seconds. Y is the amount of soda remaining. So if we interpret the slope here, again, it's always change in Y over change in X, which on this problem is going to be the change in the amount of soda remaining in the can over the change in X, which is tapping time. We're going to take the slope, which in statistics, the slopes are usually, ugly looking decimal numbers. In this case, it's 2.63. If we write that down as a unit rate, okay, this is going to tell me that for each 1 second increase in tap time, the predicted soda remaining is 2.63 milliliters. I'm filming a lesson right now. Now, there's another way you could say this, and that is you could say that we are predicting an extra 2.63 milliliters of soda will remain for each additional second of tap time. For part B, we'll talk about the value of the y-intercept, and it says, does the value of the y-intercept have meaning in this context? And that is yes, because it does make sense to take a can of soda and tap for 0 seconds. It's totally allowed. You can just grab the can and open it right off the bat. Now, in terms of what does the y-intercept mean, so the numerical value is 248.6. And that's, of course, measured in milliliters. That is going to be the predicted volume of soda if you tap for 0 seconds. All right, the least squares regression line, also known as the LSRL. This is going to be what we call the line of best fit. So, say you have a scatter plot, right? Miles driven by a Ford F-150 and the price. What's the line that best describes this relationship? Is it that line? Is it perhaps that line? Is it perhaps this line, right? What is the line of best fit? So we have to come up with some sort of statistical and mathematical idea for what it means to come up with the line of best fit. Okay, so what that means is it's going to make the sum of the squared residuals as small as possible. So what does that mean? Well, if you take this data and you look at the residuals, that's the vertical distance between the actual and predicted values. Well, statistically, the sum of the residuals will always be 0 because there's positive and negative residuals that are always canceling each other out. So in statistics, we square those differences so everything is positive. Now, if I were to move that red line around, maybe make it flatter, steeper, move it around, and we kept track of the sum of the squared residuals, or add up the area of all those squares, we want to make the area of all those squares as small as possible. Thus, when we do make this sum achieve its minimum value, we achieve what's called the least squares regression line. And that's what we mathematically agree on as the line of best fit, is the line that makes the sum of the squared residuals as small as possible. That's why it has that name. Now, using technology, how do we get the equation for the line of best fit? Well, you already know this command. If last class you did it to get the correlation coefficient, in this case, we would put the explanatory variables in L1, the response variables in L2. The exact same thing we did when we made the scatter plot, the exact same things when we calculated the correlation coefficient R from last lesson. Make sure you don't sort the data, because we want to make sure it treats 23 and 167 as an ordered pair, and make those things as an ordered pair, and makes those things as an ordered pair, etc. Now, the command that we're going to do this is you're going to go to the stat button. You're going to right arrow over to calculate. And then you're going to go down to number 8 on that menu, which is linreg a plus bx. When you select it, it's going to ask for xlist, and that's where your explanatory variable is, and that's L1. Your ylist, which is L2. Then there's another thing called like store regression equation, whatever, just leave that blank. Then go ahead and hit calculate. Same command you did last time to get the correlation coefficient. But now, in addition to the correlation coefficient, which you know about, we're now going to take the numerical values of A and B and just substitute those in for the intercept and the slope, and you have your equation of the least squares line. If you want to make sure you do this one correctly here, y hat is equal to 82 plus 3.3077x. That's the equation for that line of best fit. Okay. Now, what effect do outliers have on least squares regression lines? Okay. So sometimes outliers can make things, it can make relationships stronger. Other times it can make relationships weaker. So what child 18 is doing, this here, if you covered up without child 18, the graph would probably look more like that. It'd be a little bit flatter. So what child 18 does is it's going to make the slope steeper, meaning in this case it's going to be more negative, and it's probably going to make the y-intercept become bigger. What does child 19 do? Well, without child 19 in there, if you covered up that value, basically what child 19's impact is it's not as drastic. Might be difficult to see. What it will do is it will pull the line up a little bit, and it's going to be more parallel. Slope is not changed much. And the y-intercept will increase, but probably not much. So child 19 is not as impactful as child 18 in terms of the outlier value there. You can read a little bit more about the impact of what happens on that slide there. But this has been long enough, so I'm going to go ahead and shut this down.